All right, so in part 2 here, let's take a look at the complex exponential e to the s naught t, okay? Now, we have said that the Laplace transform is a complex function of s. So if I have x of s, right, which is the Laplace transform of x of t, okay, we have said that this s is equal to a sigma plus j omega. It's a complex function, okay? And in fact, what we ended up saying is, we'll pull up the picture here that I showed in the very first lecture. If I had a particular Laplace transform, what I'm showing here in 3 dimensions is the magnitude of that Laplace transform, which we plot as a function of s, so as a function of the real part and the imaginary part, okay? So we look at that in this complex plane, okay? So if I think about this, here's my complex plane, all right? So here's sigma, here's j omega. So this is the real axis, this is the imaginary axis. So let's think about this value here, s naught, okay? Well, we've got a couple of different things that we can look at. If sigma is a negative number, so sigma is the real part, if that's a negative number, that means that this complex number s is somewhere over here, right? If sigma is a positive number, it means that it's somewhere over here, right? Well, what happens if sigma is 0? So let's say sigma is equal to 0. So that means that s equals j omega. So that means that the number s is somewhere right on this axis, the j omega axis, okay? Now, if that's the case, let's look in general. If I have e to the s naught t, and that was equal to e to the sigma plus j omega t, that would be e to the sigma t times e to the j omega t. All right, so let's take a look and understand what that means for a second, okay? If I have e to the real number times t, okay, real number times t, there's basically 2 choices for this guy, right? If the real number is positive or negative, that completely changes this, right? So if the real number is negative, then that guy looks like this, all right? He's a decaying exponential, right? If this was a positive exponential, it's an increasing exponential function. So if the real number here is positive, this guy is an exponential that's increasing. If the real number is negative, this is an exponential that's decreasing, okay? Well, what about the imaginary term here? So e to the j omega t. Well, what you guys should know for that, okay, is the e to the j omega t, we use Euler's identity to expand that into cosine of omega t plus j sine of omega t, like so, okay? So essentially what we sort of say is that if I have e to the s naught t, this part here is really kind of the envelope of the waveform, okay? This guy right here is some sort of a sinusoid, okay? We use Euler's identity sometimes to represent cosines and sines. So for instance, let's say I have cosine 10t. I can say that's the real part of e to the j 10t, okay? Let's say I had cosine 10t plus 30 degrees times, I don't know, 30, okay? Well, I could say that that was equal to the real part of, all right, and just to maybe make that a little bit simpler, so let's say I want to say, what is that the real part of? So one thing that might be easier is you say, well, what if I had 30 times cosine of 10t plus 30 degrees plus j sine 10t plus 30 degrees, okay? You could write that as 30 times e to the j 10t plus 30 degrees, like so, okay? And you could then write that as 30 e to the j 30 times e to the j 10t, okay? Now, this number right here is sometimes referred to as a complex amplitude, okay? And if you look at that for a second, you guys might be more comfortable with writing that as 30 angle 30, right, times e to the j 10t. So that number right there, multiplying that e to the j 10t, is really a phasor, okay? Right? It's a complex number with a particular angle and a particular magnitude. That's a phasor. That's what we defined a phasor to be. So if you look at this, go back to my original question, right? I said 30 cosine 10t plus 30 degrees is the real part, it looks like, based on the analysis of everything we did here. Looks like this is the real part of 30 e to the j 30 degrees times e to the j 10t, right? Or the real part of that phasor that I just defined times e to the j 10t. Okay? All right. Well, so bearing all of that in mind, okay, let's go back to the result that we found at the end of part 1. So at the end of part 1, we said if we put, or maybe all of part 1 here for a second, I said if I put an exponential e to the s naught t, a complex exponential, into my system, into my circuit, as my input to my circuit, that had a Laplace transform 1 over s minus s naught, right? So I did my analysis over here. I said the transform of the output is equal to this guy over here. And I said to find out the real output as a function of time, I take the inverse Laplace transform of v out of s, okay? So that led us to this result right here. We said that the steady state output is equal to the transfer function evaluated at s naught times e to the s naught t, okay? So let's say we had as our e to the s naught t, let's say we had, for sake of argument, e to the j 10t. All right. In fact, I'll keep it more general for a second. Let's say I have just e to the j omega t. Okay. E to the j omega t. Okay. So if that was the case, I have, from what I have up above, that v out steady state of t is equal to h of s naught times e to the s naught t. Okay. So if my s naught was j omega, so in other words, if sigma is equal to 0, there's no real part to my complex number here. This guy here becomes h of j omega times e to the j omega t. Okay. So if I look at my h of s from above, my h of s in this particular problem was 0.1 s plus 1. Okay. So let's write that out here. So I have 1 over j omega 0.1 plus 1 times e to the j omega t. All right. So if I were to look at that for a second, okay, I can write this here as just simply a phasor, okay? And the way I would do that is I would say, well, what's the magnitude and angle of that guy? So what's h of j omega, what's its magnitude? Well, I would say it's 1 over the square root of, so I could get the magnitude of the bottom. So that's 1 squared plus omega squared times 0.1 squared, okay? And the angle of h of j omega is equal to the angle of the top, well, that's 0 degrees in this case, minus the angle of the bottom. So that would be arctan of the imaginary part over the real part, so that's 0.1 omega, okay? So if I were to look at that here, I would say the other way that I could write this is, there's a couple of ways. I could say the magnitude of h of j omega times e to the j angle h of j omega times e to the j omega t, or if you would prefer, h of j omega, and I say angle h of j omega, like that, times e to the j omega t, okay? Now, if I look carefully at this, all right, what I have again is a phasor times e to the j omega t, all right? So looking at this carefully, I know that this guy needs to be, if I look at it with Euler's identity, I can say that this guy through Euler's identity would be magnitude of h of j omega, all right, times cosine of omega t plus angle h of j omega plus j sine omega t plus angle h of j omega, okay? You may have to look at that slowly, all right? But I see something kind of interesting, because what I have is essentially a phasor times e to the j omega t. So in the end, what I get is sort of an exponential result here. Well, this is very similar to what I would have in typical impedance analysis. So let's do a quick example for ourselves, all right? So we said that in this particular case, for this circuit, all right, and let me maybe kind of repeat the circuit down here, all right? So let me bring it down. For this particular circuit, all right, what we said is that I chose R equal to 1,000 ohms and C equal to 10 to the minus 4 farads, okay? Let's say we were back in impedance analysis and I said that my input was Vn of t equal to, I don't know, let's say I did cosine of 10t, like that, okay? So cosine of 10t. Well, you would have told me that the phasor that went with that is Vn equal to, in this case, just simply 1 angle 0. Or I could write that if I wanted to as e to the j 0 degrees, okay? All right, so in phasor analysis, we would have then said that this guy becomes simply Vn R, there's a capacitor here, and this becomes 1 over j omega c, and this is the V out phasor, okay? And this is the V in phasor. Now I want to solve this guy symbolically first, okay? Now obviously in this case omega equals 10, all right? But I want to solve it symbolically. So I see I can do a voltage divider on this. So I get V out equals 1 over j omega c over 1 over j omega c plus R, so that's the total impedance, times the phasor of Vn, okay? So I can do the same thing with this that I did up above with the Laplace transform, and I want to multiply both top and bottom by j omega c. Okay? If I do that, this guy becomes simply 1 over j omega rc plus 1 times the phasor Vn. Okay? If I look at that real quick, and I plug in those numbers, I get 1 over j 0.1 times omega plus 1. Okay? So remember r times c here, rc equals 0.1. All right, so that times Vn. And wow, that looks a lot like what we saw above. This guy here, if I look at that term, 1 over j times 0.1 omega plus 1, that is equal to h evaluated at j omega. So remember, h of s was equal to 1 over s, well, 1 over 0.1 s plus 1. So if you notice the difference here, I just plugged in s equal to j omega. Okay. So notice that this relationship between the phasor of V out and the phasor of Vn is just simply h of j omega times Vn. So these guys are pretty closely and clearly related to each other. Okay? That's a really important result, which we're going to exploit here a little bit further. Now, if we had this result right here, all right, you would have gone in and you would have plugged in omega equal to 10. So again, for the particular problem we've got, you would have plugged in omega equal to 10, and that would have become 1 over j plus 1 times the phasor of Vn. Okay, and you would say to yourself, well, that is 1 over the square root of 1 plus 1, so 1 over the square root of 2, with an angle of, in this case, angle of the top is 0, angle of the bottom is 45 degrees, so it'd be negative 45 degrees, right, times Vn, whatever that phasor is, which we said in this case, that phasor is just 1. So that would tell us that the output phasor is 1 over square root of 2 time with a 1 over square root of 2 with an angle of negative 45 degrees. So we would have said V out of t is 1 over square root of 2 times cosine 10t minus 45 degrees. Okay, well, let's go back to our result up here. Okay, somehow we must be able to do the same thing. Well, if our circuit had an input of cosine 10t, I could say that cosine 10t is the real part of e to the j 10t. And what I could do is I could say that h of j omega times e to the j 10t, I could figure out what that is and then take the real part of that, and I bet I'm going to get the same exact answer. So let's try that. All right, so h of j omega times e to the j 10t. If I look at that, I'm going to get from that 1 over j omega times 0.1, okay, plus 1 times e to the j 10t. And if I look at this, we said omega was equal to 10. So I have 1 over j plus 1 times e to the j 10t, like that. Okay. So this we've already done previously. We know is 1 over square root of 2 with an angle of negative 45 degrees. Okay. That times e to the j 10t. That is the same. This result right here, notice, is the same as the output voltage phasor, right? So that's interesting, right? So if I look at this, I like to write this guy as 1 over square root of 2 times e to the negative j 45 degrees. That's the exact same thing, times e to the j 10t. So if I expand that out, I get 1 over square root of 2 times cosine 10t minus 45 degrees plus j sine 10t minus 45 degrees, like that. If I look at that result and I said, let's take the real part of that, the real part of that result, so the real part of that whole result is simply 1 over square root of 2 times cosine 10t minus 45 degrees. The exact same result we got when we just simply did phasor analysis. So what we see is something that for us is going to be kind of important as we move forward, okay? Really nothing different than what we've done in the past, but basically what I see is that V out steady state of t is equal to the transfer function evaluated at s naught times e to the s naught t. And we're going to focus ourselves particularly, so s naught can be sigma plus j omega, but we're going to typically focus ourselves if I have s naught equal to j omega, so the sigma piece is equal to 0, then I see quite clearly with that what I have, right, in this particular case, my e to the s naught t is a sinusoid, which is really the special case that we look at so very frequently in circuit analysis. All right, so we'll have more to talk about with that on Monday, and we'll start using that quite a bit. But essentially what we've just done here, just in summary, is we've taken all the analysis that we've done here with Laplace transforms, okay? And we've said, at least in this, the steady state piece of this, so where is that? At least for the steady state piece of this, the analysis that we're doing is exactly the same as the analysis we did when we did phasor analysis. Because for these complex exponentials, they are essentially just sinusoids if we're only concerned about the situation where the real part's equal to 0.